Okay, good afternoon, class. So we already have Michelle and Kathleen here right now. But Senhar, yeah. So previously you asked about joining the class, right? Just to sit in.
Yes, to have some knowledge. So I have a bit of knowledge on the next semester when I take the script.
Class. Yeah, yeah. Okay. So actually, I've already discussed it with the lecturer team, and then yeah, it's fine for you to join the this class just to sit in. But however, since you are not registered in the my UP system, then you won't get the file, the presentation files, and also you cannot like joining in any of the class activities like the assignments, the quiz, or the midterm.
Yeah, it's
Yeah.
okay, sir. I get it.
So yeah, just to let you know about this, and then now let's see, we have okay, we also have Kenneth that's already joined now, and Gabriel. All right, let's start uh, the course. So, is there any questions before we start to learn about the new topic? Is there any questions regarding last week's material about last week's topic?
Actually, I have a lot of questions, sir.
Okay, so what's your questions?
Like the last example
Mm-hmm.
that you gave us
Let me open it
about
first.
the
Pigeonhole,
the pigeonhole, the number for exercise 2.
exercise 2, number 4. Okay, all right, this one, right?
Like this is the same case. Like we have to take the 3 diamond card in the example, right?
Right, correct.
And it said that we have to take all.
No, there's in the question, it's not say that you need to take all. So you just need to determine like how many objects that must be taken from this container to ensure that first the sun-shaped object will be taken. So you must make sure like how many times that you need to take the objects until that you are sure that the sun-shaped object will be taken from this container.
So actually, how can we do that?
So actually it's easy. So you see that how many
Okay.
objects in this container, right? That we have.
Yeah.
We have 7, right? It's similar with the card example here, the bridge card here,
Yes.
right? So since you only want to take one sun-shaped object here, and then you are not sure that what kind of object that you will take from that you will pick out from the box, right?
Yeah.
Each time. So in that case, if you really want to ensure that the sun-shaped object will be taken, then you need to take it all one by one, because here you only have one sun-shaped object. So in this case, what are the other objects? The total number of the other objects. We have like 5, right?
Five.
So we have 5, and then next we we need to take the sun shape. So 5, how many sun shape that you want to take? 1. 5 added by 1, so you need to take 6 objects, so that you can be sure that the sun shape object will be
So
taken.
we have at least we have to take at least 6 objects, right?
Right. So yeah, in other words, like all the objects must be taken, but you need to provide like the arguments why all the objects should be taken. The arguments earlier I've already explained earlier, right? Since you want to make sure that this sun shape object will be taken, then you need to know what are the other objects, the number of the other objects inside the container. So you need to take all the other object first, then add up by 1 the objects that you really want to take out. So that will be the answer for this question number 4.
Oh, so for the question number 4B,
Yeah,
it means that 6 we have to
take
take 2. So I mean we have to at least take at least 6 object, all of them again.
which one? For number B, for B.
B.
Is this for B the your questions right now?
We have to take same, like we have to take 6 object again.
No, for B this one you don't need to take 6 objects. So here you see what are the questions right now. So right now you want to take, you need to ensure that 2 face shape objects are taken, right?
Yeah.
In here, how many objects that are not in the shape of a face? There are 3 other objects, right?
Yes.
2 hearts and 1 sun. Okay, so we have 3 objects that we need to take at first. And then how
3
many
object.
objects that you want to take next? 2
2.
face. So 3 added by 2. So you only need to take
Oh,
5.
so that's how to do that. So
Yeah.
we have to consider the other object that outside the question and edit by how many object we have to take.
Right.
Okay.
Actually,
Thank you, sir.
you're welcome. Actually, for number 4 here in exercise 2, it's not really about the pigeonhole. It's more like a logic.
An
logic
opportunity, right?
Yes, the opportunity. It's similar with this
is it-
bridge card example.
Yeah. Is it connected between A and B?
Between
I
A
mean,
and B,
if it's connected, like the sun shape will be taken, so the B, the question for B, the sun shape is already taken, so there's only 5 remain in the box.
okay, so it will be a different story. It will be a
Okay.
different case other than outside of this topic. So this topic what we will learn for into these lessons.
Okay, sir.
All right. It's regarding
Thanks.
like the sequence, the order. How are you going to take the objects out from the container?
Okay, thank you, sir.
You're welcome. Any other questions about the previous exercise? No? So can you guys open up your camera so I can know that you are there? Here, Gabriel here, Kathleen and Michelle. Okay, Kathleen is here. Okay. All right. So yeah, since we don't have any other questions, so we'll just start with the next topic, with today's topic. So here we go. So today we'll learn about counting and probability. So how many of you already taken statistic course?
No one, sir.
No one? So in the first semester, you are not required to take statistic.
It's on our next semester or probably our next 2 semester.
Okay, I see. So in that case, okay, I need to explain a little bit more for this topic in that case. Okay, that's fine. So how many of you ever heard about the term probability? So surely that most of you are graduated from the science department, right? In your senior high school. So I believe that all of you already familiar with this term called probability. So yeah, so in a very brief explanations, in a very brief definitions for a probability, it's just showing you a numerical value to show the chance of something to occur, right? So it's similar like when I give you a coin, so I ask you to toss this coin. So what are the chance? What are the outcomes from that activity? So you can only get two kind of there are two outcomes, right? So the coin will show up heads or tail, whether it shows up a number or the value of the coin, or like maybe some picture, right? Yeah. So yes. So the first term that we need to learn, that we need to know, is regarding experiments. So to all of this is related with experiments. So experiment itself, there it is an observations towards a data gathering process that have various possibilities of results. So from this observation results, then you can come up with reasoning, like what are the chance for something to occur. Let's say like earlier, when I give you one coin, what are the chance of the outcome? You will have only two outcomes, right? Whether it will show up head or tail. And then what are the chance for these outcomes to come up? Both of them have the same outcome. Both of them has the same chance, right? 50% it will show up heads, 50% it will show up tails. Okay, so yeah, so basically, experiment itself in the statistic and in many of the observations. So usually you will be asked to do a random experiment. So this is a random and deterministic experiment. So I'm not going to talk about the deterministic experiments since it's quite boring. But the most interesting is about the random experiments, because it is random. Sometimes it will be unpredictable. Sometimes the results you cannot really predict. They cannot produce the same exact result every time. There is some possibility that the result from the experiments that you perform will vary from one to others. So, however, you need to make sure, you need to ensure that when you are performing these random experiments, there are two basic assumptions. There are two basic characteristics that you need to hold. The first one is the experiment that you perform, no matter how random it should be measurable. Measurable. It means that you will know uh, how will you coach, how will you evaluate the value that you can obtain. How can you evaluate the result that you get from these experiments? And also the second characteristic, you should be able to do it repeatably, repeatably, right? Multiple, more than once. So these two are two basic characteristics of random experiments. So for examples, earlier I have already told you coin tossing activity and also throwing dice. Okay, even throwing a die is also counted as an experiment. Also, another real world example is when you do a customer satisfaction survey. So maybe you have some experience when you visit, like let's say a customer service of a bank, or maybe a customer service of a company. Then after you ask them some questions, or maybe after you ask them to help you to do something with let's say in a bank. Okay, let's say you want to open up a new time deposit account in a bank. So you need to visit a customer service officer in that bank, right? So later on, they will give you ask you to give the data, maybe it's like your identity, and then it's like how much amount of money that you want to store in this time deposit program, right? So after you go through everything, and then after the officer, the customer service officer, explain to you what are the steps, what are the procedures, then at the end, probably maybe some of them will ask you to give them a rating, to give them whether the service that they provide to you are clear enough. So in that case, uh, this kind of activity itself can also be observed, right? So in that case, this is also can be considered as a random experiment. First of all, why it is called random, not a deterministic? First, you as the customer service officer, you cannot enforce your customers to give you like the best result, right? It's possible. Let's say if in the survey later on, usually your customer will be given like a questionnaire using like a scale. Let me remove this two first. Okay. Okay, so probably so your customer will be given some questionnaires using a Likert scale, or like starting from 1, denoting the worst service ever, until 5, showing the best service that they can provide to you, and 3 being neutral, right? So in this case, the customer service officers, they cannot predict what value, let's say, that you will give to them, right? You can give them like 5, showing that they give you she or he gives you a perfect explanation, a perfect service, or maybe you think that the service that they provide to you, they are not good enough. So therefore, maybe you give 2, or even worse, 1. So they cannot control this. So that's why this is also called as a random experiment. And then another thing is observations on stocks price exchange. So for this one, it's also considered as a random experiment. So, okay, so the value, the price of a stock that a company has, they usually fluctuate, not day by day, but by every seconds, by every minute. So in that case, let's say you as a stock investor or maybe a stock trader, can you make a guess that the price will always go up? That the price at that time, like for example, for one session or for one day, a specific stock price will always go up, will always rising up in the price, or maybe the price will always go down. No, right? You cannot make this kind of predictions. If you make this kind of a prediction, if you make this kind of a judgment regarding this stock price, what does it mean? It means that you are speculating on the price of the stock. Okay, so I will not talk much details again about this one. This is just an examples that I want to give you so that you will know like what activity that can be considered as a random experiment. So even in the real world, like in the day by day of your life, you will always notice this kind of random experiments activity. Right. So regarding that, we already know that we have the experiments. So of course, there from that experiment activity, you should have the outcome, the results. So when you are doing observations, so remember what are the basic characteristics that I've just mentioned earlier. It should be measurable. If it can be measured, then what does it mean? So it must produce some kind of result to you, right? For the researcher, or maybe for the one who do the observation, the observer. And also there's another term called sample space. So what is it? Oh, okay. So here you can already see the explanation for the outcome itself is any possible results of an experiment or a trial. So usually when we talk about outcome, then we will talk about a singular value. So for example, here you perform one kind of experiments like earlier, a questionnaire, customer satisfaction survey. So from one customer, how many outcomes that you can get? It depends on the questions. Okay, let's talk things into much further detail. So for one question, what are the outcomes that you can get from one customer? You can only get one outcome. You can only get one result based on the question, right? If the question is in the type of using Likert scale, like from the scale of 1 to 5, your customer can only give one result to you. Okay. So sample space is the set of all possible outcomes. You can think of a sample space as a collection of outcomes or the results of that experiment. So let's go to this previous experiments like a coin tossing here. So here, what are the outcomes? Anyone can give me some response?
Head and tail.
Head and tail. Okay, that's correct. Earlier who? Kathleen, right? Yeah. So the outcome for this coin tossing, it can be head or tail. This one is correct. How about the sample space? Move this picture somewhere else first. Okay. So for the outcomes here, like I mentioned earlier, it should only have one value, either it's head or tail. So what about the sample space?
Is it a half? No.
Sorry, Kenneth?
Is it a half?
All,
A half?
half,
No.
half of what?
Half head, half tail.
Half head, half tail. Um, Not quite correct, but it's almost. So for the sample space here, remember, one thing that you should remember for the sample space is the set of all possible outcomes. So it's a collection of your outcome. So if previously I mentioned that for the outcome, it should only have one value, one possible result, a possible result. It means you only have one value. So for the sample space here, you should mention all kind of the value that you have. Let's say in here, assuming that the result for one experiment is head. Okay. Experiment one is head, and then let's say for experiment two, you get tail, right? So it's impossible for you, let's say in the experiment one, you get both head and tail just from using one coin. This kind of thing is impossible to happen unless you use two coins, right? So in this case, so the sample space of a coin tossing just using one coin should be head, comma, tail. So you list out all the possible outcomes here in your sample space. So if, let's say this, I change to another example, tossing two coins. So what are the outcomes?
Head tail,
Okay, head, tail.
then head.
Okay, so I spell it with a semicolon here to show another experiment, right? Head, head. Okay, is there another or just this?
Tail head
Tail, head.
and
All right.
tail.
Tail, tail. And what? Yeah, this is for the outcome here. It's correct. How about the sample space? Thank you, Gabriel, for earlier answers. Then the next question, how about the sample space here? You already have 4 possible outcomes here. Head, tail, head, tail, tail, tail.
Is it head tail and head tail, sir?
Head, let's see here, head, tail, and head, tail. Is this correct, Kenneth? Is this what you mean?
Is it? I mean, oh, I don't know. I'm not sure about that.
Uh-huh. So it's okay. So what's your opinion? So is this your opinion,
Yeah,
or
that's my answer.
that's your answer? This your answer? Okay. So any other opinions from the other students? Yeah.
Just as before,
Okay.
head, comma, tail.
Just like before, head, comma, tails. Let's copy this. So we only have like head, comma, tails here. Okay, this is from Kathleen. So any other opinions? Gilang, Michelle, or maybe Senhard?
Not yet sure. Still figuring out.
Okay. Okay, so like I've already explained earlier, so for the sample space, you should put all the possible outcomes into your sample space here. So let's discuss from Kathleen's answer here. So according to Kathleen, the sample space only consists head, comma, tail. It means only head and tail. So basically, this will be correct if you use only one coin. But if you use two coins, so here, earlier your friend Gabriel already explains what are the possible outcomes here, right? There are 4 possible outcomes: head, tail, tail, head, and tail, tail. So in this case, you should come up with a pair, not only just one value here, because you use 2 coins. So if the first coin is head, then the coin number 2 would be tail, might be tail. But there are also another possibilities. Let's say if you get head tail again, you don't need to write it up again in the sample space because you only need to write once. Okay, so in that case, you will have tail, and then another possibilities is and head. Okay, and then you see here what are the possibilities that we have. We have head, and tail, tail. This one, head, tail, tail. So the sample space for this experiments, tossing 2 coins, will be like this one. You need to write everything: head, tail, head, and tail, tail. So what if, again, let's say if I change this to tossing 3 coins? So similar. So you need to add up the another possible value for the third coin here. Let's say this one, head, tail, and head. Or maybe this one, head, head. So for, yeah, etc. Right? So I don't need to finish everything. Later on, you can figure it out. For this one, of course, I need to add up another head, since now we use 3 coins, right? The first coin, second coin, and the third coin. Okay. Yeah. Yeah, similarly, so this is also another examples. Another example, for example, throwing a die. So you know that for a die, it has, for a normal die, it has 3 sides, right? Showing the eye of the die starting from 1, 2, 3, 4, 5, 6. So when you throw one die, so it can come up with either 1, 2, 3, 4, 5, or 6. It is not possible, let's say, how can I rotate this? Okay, let's say here, when you throw up this die, and then this die land on the ground in this position, showing two sides. Is it possible for a cubic dice? No, it's not possible, right? So you always come up with one value that's showing on the upper side. So the outcome, it can be either 1, 2, 3, 4, 5, or 6. And then what about the sample space? Then you need to write all the possible options. 1, 2, 3, 4, 5, 6. And don't forget, usually for the sample space here, it will use the symbol S here, capital S. And then you need to have this curve bracket, opening curve, and then what are the values, and then closing with another curve bracket. Okay, so another experiment, picking a card from a deck of bridge cards. So what are the outcomes? So it can be any one of the cards from these 52 different cards. Since the 52 cards in a normal bridge deck, they are already different. So for the sample space here, I only give some examples. I don't list out all the possible solutions. So it can be like 2 spades, 3 spades, 4 diamonds, 10 clubs, jack of hearts, and the other cards until you get the 52 cards are listed out in this sample space. Okay, so far, is there any questions about the about random experiment, outcomes, and sample space? No. Okay, it's very easy, right? Then we the sample space itself, it has 3 types. The first one is a finite. What does it mean? For finite, it means that it is limited. It has a limit in the number, and also you are able to count the value. For example, here I have a sample space here like 1, 2, 3 cosinus of pi divided by 6, or this is cos of 30 degree, and then sinus of pi divided by 3, sin of 60 degree. And then let's say 6 is element of S. So the symbol E here, it means element. So 6, you can find 6 inside this sample space. So for the finite sample space, it is countable, measurable, it has a limit. Okay, so another example here, this one, the second part here, if you can see the one that I highlighted, this is the sample of the previous experiments, tossing 2 coins. So T denotes for tail and H denotes for head. So what are the possible sample space? Since you use 2 coins, then there are 4 possible outcomes. Tail, 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 head, head, tail, head, head. And then let's say tail head here is an element of your sample space. So the second type of the sample space is countably infinite. So infinite, it means it does not have any limit. It can be any possible value. Okay, but since it is countable, you need to be able to measure it. You should be able to count it. For example, here, the sample space here is a sample space of natural numbers. Let's say from 0, 1, 2, 3. So what are the limit of natural number? So you don't know. You don't know the limit for that number, right? So it can be 1 billion, it can be 1 trillion. Okay, it can be uh, quadrillions, right? So since you don't know the limit, since you don't know the limit for this sample space, so this sample space is considered as an infinite sample space, but it is countable. So let's say you can pick any value that is not inside the sample space that you have written here, but as long as they have the same characteristic, then you can say that this value is an element of this of sample space S. Let's say here, I give you 580, but if I want to change here to 5 billions, I can still say that 5 billion is an element of sample space S here because they still have the same characteristic. It's still a number. It's not a floating number. All right. So another example here is tossing a coin, but I don't give you some limitations like how many coins that you should keep. Okay. So as long as, let's say, the last coin shows up tail. Let's say you toss one coin. If the last coin should show up as a tail, so it means what? So it the value would be only tails. If you toss up two coins, then the first coin should show up head, and then the second one show up tail. Like this one, 3 coins, head, head, tail. 4 coins, head, 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 tail. And then you see here, how can I say that the last coin should only shows up tail? Because here, you can see here in the second part, TH, tail and head, is not an element of sample space S. So that's why tail should never come up from the first coin. But I add up, there's another explanation here. So let's say this we have 4 head here. Let's say if I have like 10 head, let's say add up like this one, this still should come through because the requirement earlier is only the last coin should shows up as a tail. Okay, so another type is uncountably infinite. So what does it mean? It is the most ambiguous one of the sample space. So the elements, the member of the sample space is already infinite. There is no limit already. It's a very huge. And added up by another characteristic, it's uncountable. You cannot count it, the member of it. So it's not that not a fixed number. Okay. For example, here sample space has the element of the sample space S is theta, where the value of theta it can range starting from 0 until 2 pi. Here, where pi is still an element of sample space S. So can you determine what are the value of theta? So theta can be like 3.14 or the value of pi itself. It can be 3.145. So here you need to be careful. 3.14 and 3.145, they will be seen as a different element in this type of sample space. Okay, so another example here, I have a sample space S, and then in this sample space S, it has a coordinates value, X and Y, where the value of X should be greater or equal to 0, but less than Y. And then the value of Y itself should be greater than or equal to X, but less than 2 pi. But you might not know what are the value of X and Y. You cannot determine it, right? They only give you like this kind of characteristic. So here, let's say 5.4 comma pi is an element of this specific sample space. It's possible if you are talking about the pi here is 180. Right, so these are 3 types of sample space. Okay, so we have this exercise now. Let's see how many. Okay, we have 2 exercise. Okay, let's quickly do the first exercise here. A company has branch offices in 6 cities, Surabaya, Malang, Jakarta. Yeah, and a new employee will be placed in one of the 6 branch offices. So what is the experiment for this case? So can someone volunteer to answer these questions? So who wants to volunteer to answer these questions? Question A.
That Surabaya, Malang, Jakarta, Bandung, Ujung Pandang, and Medan. All of them, sir.
Mhm. This is the which one? A or B? Earlier.
For I think both of them same.
Both of them are the same.
Yeah.
Okay. For here, for the sample space here. See. For B here, the answer will be this one. So for B is correct. So what about A, the experiment here? So you see here, the experiments, they should show up what are the activity that is being done in that question. So actually for A here, the answer, the experiment is not Surabaya, Malang, Jakarta, Bandung, Ujung Pandang, Medan. But what is the experiment?
The new employee placed in Surabaya.
Right. Not in Surabaya, but it's more appropriate to say new employee placement experiment. See, you need to come up with some kind of a noun to show, just to make brief conclusions, to summarize about these questions. So what are the experiments? You need to think of what kind of activity that will be carried on in these questions. So this will be the answer for question number 8, the experiments here. So the company have this branch office, a new employee will be placed on this. So obviously the answer will be related with this one, right? So you can just directly say that a new employee placement experiment. This is the answer for the experiment. For the sample space, it's correct. What Kenneth had said earlier. So the value can be Surabaya, Malang, Jakarta, Bandung, Ujung Pandang, and Medan. Okay, we go to the second questions. So tossing a coin is selected as a way to resolve disputes among members in a group. Then what is the sample space of this experiment?
Is it head, comma, tail, sir?
Right. Thank you, Gabriel. Yes, the answer here is correct. Only head and tail. Why? Because here, from the questions, you can know that you only use one coin here. Okay, so let's go for number 3. Consider 4, the same questions, but if the number of coins becomes 2. So what are the sample space? Yeah, actually, it's similar with the previous examples that I have already uh, showed to you earlier. So yeah, so you can think, let's say head, tail head, and tail, like this one. So you can use this kind of abbreviation, but please don't forget to mention to describe what HH means. What H means here. So here you need to add up more explanation. H is head. and T means tail, this one. So to let others to understand your answer here. Otherwise, they need to guess what does HH means stands for. What does HT stand for? Okay, all right. So there's another term called event. Event. So event itself actually is a subset of a sample space. It denotes one type of the activities from your experiments. So for example, here we have an experiment throwing a die or tossing a coin. So you can think of any kind of experiments. And then let's say the experiment throwing a die, you have the sample space 1, 2, 3, 4, 5, 6. So let's say I have one event. Okay, the event here that I mentioned, odd number of dice eyes shows up. So what will be the value of this event? So usually for event here is symbolized using E here. So here you know that odd number of dice I shows up. So it means since E itself is a subset of a sample space, it won't be the value should come from this sample space. So the value here, you already have the requirements, should be odd number. Then here from 1, 2, 3, 4, 5, 6, we have 1, 3, and 5. That are the odd number. You cannot have in here, let's say, let me think, let's say 13. Here, let's say I have not 5, 1, 3, 13 here. Is this correct? Even though all of them are odd numbers, 1, 3, 13, they are odd numbers, but they are not a subset of your original sample space. So what are not the member of the sample space? Obviously, 13 here is not in an element of the subset. So that's why the real element here is incorrect. All right, so we go back to our previous exercise. So a company, yes, similar, has 6 brand offices. So what are the event of this experiment if the new employee will be placed in East Java?
Obviously, Surabaya Malang, sir.
Right, that's correct. Thank you, Kenneth. So I don't have the answers. I haven't read the answer already. So here, remember when you write this kind of event, you need to write the symbol E equal to Surabaya and Malang. Yeah. So this is the solutions of these questions. Any questions so far regarding event, outcomes, sample space, the type of sample space? No, right? So, okay. Yeah. For the event itself, it can be categorized as a simple event and also complex event. So simple events is usually the outcome for this type of events only has one characteristic. So, and then for the complex events, obviously since it's complex, so it has multiple characteristics. It should be more than one. It can be 2, 3, 4, 5. Okay, uh, and so on. So for example, here I have 5 kind of events. Let's say events 1 here. From a group of people, male participants were chosen. So this is one type of simple event. Why? So the selected participants, they have the same characteristic. All of them are male participants. This one. How about B? Selected participants are older than 20 years old. So the keyword is this one. Another event, if the chosen participants have 3 credit cards. This one. So my questions here for this kind of events, if a participant has, let's say, 5 credit cards, will he be selected?
Can you repeat, sir?
Okay. All right, let me repeat it again. So consider this event, event C. The selected participants have 3 credit cards. So coming up from the previous 2 events, male participants older than 20 years old, and then the selected participants here, they have 3 credit cards. My question is, if a male participant older than 20 years old, but he has 5 credit cards, will he get selected in this event?
Yes. Yes, sir.
Have 5 credit cards. So this is still get selected in here.
Yeah.
B and C. Okay. So according to Kenneth, how about others? Hilang. So can you give me some response?
Yes, sir, I am here.
Okay. So what about these statements? So will this statement holds true for this event?
Pardon, sir?
So I have these statements here. Will these participants will be selected in event C? Earlier, Kenneth said that for these participants, he will be selected in this event C. Okay, let me just do a quick survey. Okay, a yes or no answer. So how many of you think that this statement, these participants will be selected in event C? The requirement in event C applies to these participants. How many of you say yes? Or in other words, agree with Kenneth? Let me call one by one then. Gabriel,
I agree with Kenneth, sir.
agree with Kenneth. Okay. 2 says yes. How about Senhar?
Well, I say yes because it's gonna be possible.
Okay. Kathleen.
No, sir.
Kathleen says no. Okay, so we have no. Okay. How about Gilang? We return back to you. Your 3 friends say yes. 1 says no.
The 5 CCs are the 5 credit cards, right, sir?
Right. CC means credit card. This one. So will you choose yes or no?
There's a possibility to get chosen.
There's a possibility to get chosen. It means yes, right?
Yes, sir.
4. Okay. So all the male students say yes. How about Michelle, the last student in this class, and coincidentally, a female student? So will you agree with the other male students or will you support Kathleen? Michelle, are you there? No response. Okay, so
On the chat, sir. On the chat.
oh, on the chat. Sorry.
I think she will answer
Oh,
from
see.
chat.
So you answered yes. Okay then. Okay, thank you, Kenneth. So 5 say yes and only 1 say no. All right. So the answer is for these participants, he will not get selected if these events apply. So this will not get chosen if event C apply. Why? Here. In here, the statement says have 3 credit cards. In here, it not says that have at least 3 credit cards. If the statement here have at least 3 credit cards, then it is correct. These male participants older than 20 years old have 5 credit cards will get selected. But since it's only have 3 credit cards, obviously these male participants will not get chosen. So yeah, Kathleen is correct. Okay, so yeah, another red card is picked from a tag of bridge card. Ace card is picked from a tag of bridge card. So for the red card here, then what does it mean? So we will have how many outcomes for these events?
26, sir.
Correct. Thank you, Gabriel. And then for this one, S card is picked from tag of bridge card.
4.
Correct. Thank you,
13.
Kathleen. No,
Is
actually
it 13?
four.
No.
No, ace.
Oh, A.
Ace
Okay.
card. It's not a spade, not a club or clovers. So ace card, we only have 4. Uh, ace of spade, ace of club, ace of heart, and ace of diamonds. All right. Okay. So yeah, we go through to the complex event. So for complex event, there are 3 types: the joint event, compound event, and complementary event. So for joint events here, the keyword, the characteristic here is if there are 2 or more events. Since it's a complex, it should be 2 or more. So the characteristic, the distinguishing characteristic here for a joint, this several events, they are occurring together at the same time. So in other words, let's say event A and event B, and maybe let's say event C and event 4. So all the requirements, they are applied at the same time. They apply together. The second type is compound events. So 2 or more events, when they are combined, it has more than 1 possible outcome. So what does it mean have more than 1 possible outcome? So the requirement from event A can apply, or the requirement from event B can apply. It's also possible for both conditions from those 2 events they apply at the same time. So if you are talking in using propositional logic, then so earlier you already learned about propositional logic, right? So conjunction, disjunction, implication before the midterm. So I hope that you still remember what this basic logic. Yeah. So you can think of joint event here is similar using conjunction, using and. For the compound here, you can think of it as is using disjunction, event A or event B, or it can both event A and event B apply. And also complementary events in which one outcome can only happen if another does not. So what does it mean? So I will explain about this complementary events later on. Okay, so don't let the definition here confusing you. Okay, so for joint events, two or more events are occurring together. So usually for this type of event, for joint events, you will create a new elements, a new sets, a new groups that has both characteristics from the two events or from the three events together from the combined events. Let's say you have two events here, event A and event B. So when you join these two events together, you will have one, you will create one group, a new group here. If you see the purple color here, the group that comes from the intersections of these two events, this is the new group. This is the intersection, it's called intersections of event A and event B. Let me, let, let, okay. Everyone can see it, right? So this, all right? The purple color, the purple area here, the intersection of these two events, it is called the intersections of event A and event B, a combinations of event A and event B, but they are not combined together. Event A still has its own characteristic, event B still have its own characteristic, but it's possible for the member of event A and event B to have the characteristic of each other. Okay, so for example here, red is card from attack of bridge card. So the statement here is looks like similar with a simple event, right? Only one normal sentence, but if we think it through, actually it has a compound meaning. It has a complex meaning. So if you think it's true, so how many red is card? You only have two, but they have two different characteristics. The first one is of heart, and the second one is ace of diamonds. So even though both cards they are ace, but they come up from different groups. The first one is from the card heart cards. The other one is from the diamond cards. All right. So yeah, like this one, male older than 20 years old are picked among a group of people. So it's already a complex event. First one is male. The second requirements older than 20 years old. Like in these previous examples, if I have male older than 20 years old and also another have three credit cards, you see, earlier I have already combined three simple events to become one complex event in the type of joint event. Okay, so compound events. To next, compound event is if there are two or more events combined together and able to produce multiple possible outcomes. So, for example, you can think of it in using English. You can think of it as event A or event B using or. For example, S card or red card are picked from a deck of bridge card. So this is the illustration. So from the 52 cards, you can pick either any red card or ace card if you want to pick a black card. So the last one is the complementary event here. Okay, so the formal definition for this complementary event is event in which the outcome can only happen if one does not there. Yeah, if one does not a member of a specific event. So let's say here I have event A here. So remember, event is a subset of a sample space S, right? So what is the complementary events of event A? So usually it will be symbolized with this character. Let's say, what are the symbol of your first event? So here we have event A. So I have A, and then come up with complement C here on top, on the right hand side, top right hand of A. AC. It means A's complements, the complements of event A. So for example, here in English, we can think of it like not any S card is picked from a deck of read card. So what does it mean? You can pick the other 48 cards from one deck of read card. Yeah. So far, is there any questions about this type of events? Simple events, complex events, or you guys are bored with the explanations because it is too easy. It's too easy. You guys want more challenge, or
Oh, that's enough, sir. No,
you know?
that's enough.
Okay. So yeah, if you can have any questions, please don't hesitate to raise up your hands. Not literally raising up your hands, but you can click on the Zooms like to raise your hands to ask the questions. Yeah, don't hesitate to like cut in the middle of my explanations if you find something is unclear, right? Okay, so I will continue with the properties of events. So the first properties is mutually exclusive properties. So what does it mean? It means if event A or event 1 occurs, then event number 2, event B, will not occur, and vice versa. If event A occurs, then event A will not occur. So for example here, the occurrence of even number shows up versus the occurrence of odd number shows up in an experiment of throwing a die. So you cannot get like number 1 and 2 at the same time, right? If you say that an event saying that only an odd number will shows up, so it means you only have 1, 3, and 5. You will not have the other way around. So usually for these mutually exclusive events, they don't have any intersection at all. So if, okay, let me borrow this picture here. This one. Okay. Group it. Okay. So let's say I have two events, they are mutually exclusive. So what does it mean? They don't have any intersections. If event A occurs, then event B will not occur. So it means that both event A and event B, they are independent to each other. They are not dependent. They don't have any relation at all. Their only relation is that they are exclusive toward each other. So therefore, in the mathematical notation, in some textbook, in some reference, usually you will see these notations. P, usually P denotes for the probability. P of A intersects with B. Usually will equal to 0 or empty elements. empty set. So A intersect with B, you don't have anything. So this is the mutually exclusive characteristic of an event. Okay, the next properties is collectively exhaustive. So for this collectively exhaustive, is one outcome in the sample space must occur. So what does it mean? So uh, it means so at least one outcome from your sample space, you will find it occurring in the results of your observations. To throw it back to send it back. Okay. Okay. So as for this one, at least one outcome in the sample space. So it can be the outcome can come from event A or come from event B. It's also even possible that the outcome is between the intersection of event A and event B. This is the collectively exhaustive one. And then, yeah, the basic rules of sample space here, it's only have two basic rules for a sample space, multiplications and addition. For the multiplications, let's say experiment number 1 has m possible outcomes and experiment number 2 has n possible outcome. So if these two experiments were performed simultaneously, then there will be m times n possible outcomes. So for example, here, let's say you have two coins, you toss two coins together. So what are the possible outcomes? You will have four possible outcomes, right? From coin number 1, you have two possible outcomes. From coin number 2, you have two possible outcomes. And then when you toss these two coins together, you will get 2 times 2, you will have four possible outcomes. Like earlier, head, 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 tail, head, tail. So this is the basic of multiplications rule of the sample space. And additions here similar. Let's say two experiments, they have the respective possible outcomes. Let's say m and n. So for addition here, it applies like this one. If only one experiment was performed among these two experiments, then there will be m plus n possible outcomes. So here you need to be careful. There is a distinguishing characteristic between multiplication and additions. So for the multiplications of sample space here, so the two experiments, when you combine them together, they need to be performed simultaneously at the same time together. But for the additions here, you only be given the chance to perform one experiment. You should only take one experiment. You should only perform one experiment from several possible experiments. Let's say from 5 experiments, you should randomly choose one experiment. So you need to add up the outcome from the experiment number 1, experiment number 2, 3, 4, and 5 all together. Right. So here's the next examples. Okay, so 7 courses are offered in the morning sessions and 5 courses are offered in the noon sessions. So how many options that a student has to take one course in the morning and one course in the noon sessions? Okay, this is question number A, and then question number B, how many options if the student has to take only one course? So can someone give me a response for these examples? What are the solutions for this example?
35.
Sorry, Kathleen.
35.
35 for A or B?
35 for A, 12 for B.
5A, this is 12. Any other answers? No. Yeah, it's very clear, very obvious from the questions. Yeah, this is correct. So for number one here, so it's easy. You just need to multiply 7 with 5 because the students can take 1 out of 7 and 1 out of 5. So the students can come up with 35 possibilities of course. This one. But if the students has to take only one course from either the morning or the noon sessions, then the students only have 12 selections, 12 for possibilities. This one. Okay. Any questions so far? No, it's still very easy, right? So if we go through this phase, then probably we can finish up in less than 3 hours. Okay, so permutation here. So in a very loose definition for permutation is a set of an arrangements of a members of a set into a sequence or a linear order. If the set itself is already in an ordered manner, either in ascending or descending order, then the permutation itself is a rearrangement of its elements to different arrangements, to a different sequence. Okay, so let me rephrase it in a formal definition of permutations. So permutation itself is any possible arrangements or combinations that you can create, that you can make from an object with regards to its sequence. So here you need to be very careful for permutation. The keyword here, this one, you need to consider the sequence or the order when you create the arrangement, when you create the combination. Okay, let's go back to the previous examples here using last week exercise. Okay, number 4. This one. So can everyone see my screen? Exercise 2, number 4 from last week. All right. So earlier, Kenneth asked, what if here for number B here, two face-shaped objects are taken, but after the sun-shaped object are taken. So what does it mean? So the order will be you must, not need, you must take the sun-shaped object first out from this container, and then afterward, it's up to you whether you want to take heart or face, or maybe heart and face or face heart face, or maybe face directly. So this is called permutation. So you also need to consider about the arrangements, the sequence when you take the object out or when you do this kind of arrangement. Let me go back to this again. Okay, so yeah, basically I understand how the students feel. So probably most of the students they will be very bored to remember the definitions, the formal definitions of a permutation itself or the loose definition of permutation. So usually the students will just prefer to remember what are the formula to solve this permutation problem. Okay, so I also give you directly the formula to solve permutations problem is usually denoted by in this form P n of n. So n permutations of an object, of an element. So it will end up with n factorial. So I'll give you an example. So here's how many arrangements can be made to arrange 3 different characters. For examples, A, B, and C. How many arrangements? Here you can have A, and then B, and then C. Remember asking for arrangements and also with regard to the sequence or the order of your arrangements, then you need to list out all the possible arrangement here. Like A, B, C, A, C, B here, they are different. And then you have like the second character, let's say the second character is B, you have BAC or BCA, they are also different. You have CAP, CPA, they are also different. So in this case, okay, this one, let me just close this one. Okay, let's just the foolish way to do the number of how many permutations, how many combinations that you can have. The way that you can do, you list out, you write out one by one every possible arrangement, every possible combination. So from here, you can find that it is 1, 2, 3, 4, 5, 6. You have 6 possible arrangements. Similarly, if in the programming, let's say, so you know that in the programming there are some requirements, how many possibilities that might that can occur. Then in that case, you need to write up the if case statement for your program. So the foolish way for you to do that is you list out all the requirements one by one. Let's say if A, then what? If B, then what? If C, then what? If D, else if E, if F, if G, if H, up to all the possibilities that you have. This is the foolish way to do that. But there is a much clever way for you to directly know like how many possible outcomes that you might come up with. So here you already know that we have 3 different characters, right? So let's say for the first character here, what are the options that you can take? For the first character, you can pick any 3 of the character, right? So that's why you have 3 here. So what about the second character? Let's say here you already pick A, then for the second character, you can only come up with either B or C. So you have 2. And then the last character will be the last one. You have 1. So multiply all of them, you get 6 possible combinations, 6 possible arrangements. So it's similar with 6. Coincidentally, it's equal to the factorial of 3. 3 factorial is 6. So if you are kind of bit of lazy to list out one by one, so you can just directly come up with using the previous formula here to come up with how many possible arrangements that can be resulted in from these combinations. Okay, how many possible queue arrangements that can be made from 5 people?
120, sir.
130, right, correct. Yeah, so 5 factorials, you get 120. So there's another type of permutations known as partial permutations or k permutations of n. So what does it mean? So for these partial permutations, you need to create any possible arrangements, any possible sequence. that can be made from k elements, in which these k elements, they are a subset of an n set. So let's say you have a set that have 5 elements. Then to do a partial permutation here, you need to pick up any number less than 5. It can be 4. You can choose 4 arrangements or 3 arrangements or 2 arrangements. If one, then there's no other story why you want to bother to create this kind of arrangements, right? But yeah, so usually you will not choose like 5 out of 5. If it's let's say if you have 5 elements in a set and then you choose to do 5 permutations of 5, then what does it mean? It's simply similar with you to perform the normal complete permutation here. So for partial permutation here is usually also known as a variations or sequence without any repetitions. So in other words, for the normal permutations, then it's possible for you to, for there is to be any repetitions to occur. So in here, the formula will become like k permutations of n, k elements permutations of n sets. It will become n factorial divided by n minus k factorial. So in some reference or some lecturers, they prefer to write this k permutation of n in different symbols, like this one. I've already list all of them one by one here. So please don't get confused with the way how other people write the symbols. So all of them here, they are the same. So some people prefer to use to write in this manner using k permutations of n, pk, and n. Some people will just use like this form. This one, p, n, comma, k. Some people will just use p, n, comma, k, like this one. So I hope that you don't get confused. It's just a difference in the writing style. But for me personally, I prefer for you to use this form. This one is much clearer. Okay, so another example here. How many arrangements can be made to arrange 2 out of 4 different characters, such as A, B, C, D? So here we already have a partial permutation. So we have AB, AC, AD, then BA, BC, BD. So here you know that AB and BA. So it's similar, but in the permutations, the sequence, the order is important. So AP and PA, they are different. Similarly, like CA, and AC, they are also different. So if you list out one by one, you will get 12 possible outcomes, right? But if it's like just only an assignment or you do leisure computations, it's fine for you to list them out one by one. If the element here only consists a small number. Let's say here, I'm going to change. Let's say this one, I want to have 15 out of 26 different characters. So how are you going to solve the questions then? Are you going to list out them one by one, A, B, C, D, until you have like all the 26 different characters from A to C, and then you have list out 15 possible combinations like A, B, C, D, E, F, G, H until until O, and then another A, B, C, D, and then the last character is not O but P. Do you do it in that way? No, don't do it in that way. I beg you. It's a waste, too much waste of time. So you can just directly use the formula. So use k permutations of n sets. So the number of n here is 2 out of 4. So the number of n is 4. The number of k is 2. 4 factorial divided by 4 minus 2 factorial equal to 12. But if I change it to 15 and 26, then it will become 26 minus 15. Okay. 26 minus 15, then 11 factorial. Okay. Yeah. So it will becomes like this one. And what is x, 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 x? So you can count it by yourself later on. Any questions so far? No? Then I'll just continue. So yeah, there are, let's say there are 2 basketball players from the engineering faculty of Upaya. They will participate in Upaya Games 2022. So the coach must choose the 5 best players as the starting members for each game. So how many possible formations that the coach need to come up with, considering each player's abilities and positions? I don't know, maybe in ULS you can already find the similar slide, but it is in Indonesia. But I'm not sure if it's already, if they have already have the answers for this one. So what are the numbers of formations that the coach needs to come up with?
$95,040.
Yeah, yeah, actually there's already the answer over there. It's fine. Yeah. So yeah, after doing the calculations, thank you, Kathleen. So you will get this number, 95,040. Okay. So how to do a quick way to do this kind of a competition. So I hope that you can just do this kind of cross multiplications, right? 12 factorials is equal to 12 times 11 times 10, 9, 8 sevens, and then times 7 factorials. So you can just eliminate these 2 7 factorials and then multiply all the rest of the elements together. Okay, so another types of permutations is circular permutations. So for circular permutation here, it means any possible arrangements that can be made to arrange an object in a circular manner. Still, since we are talking about permutations, then it means that we need to consider the sequence, the order of your arrangement. So in that way, the previous two formula earlier, it will become like this one. P, permutation of an objects in a circular manner will become like n minus 1 factorial. So remember, the 2 circular permutations are equivalent if one can be rotated into the other, that is cycle without changing the relative positions of the elements. So if earlier the previous 2, the complete permutations or the partial permutations, they are more likely talk about the linear permutations. The sequence or the order are formed in the linear structure. You have a point A and point B, like let's say here, assume this line. assume you have this line. Okay. For this line, you will have point A here. Okay. And then similarly, you can have point B. So the earlier permutations, it talks about a linear permutation. You have two different points, so that's why the order are much more important. But if these permutations are changed into a circular structure, so let's say here, let me change. Okay, let's say I have a circle here. Okay. Assuming I have a circle, and then I have at one point I have point A over here, and then point B over here. Right? So no matter how many times you rotate this circle, the order will always be similar. A, B, B, A, B, B return to A, right? So they don't have any conflicting as long as the rotations they are similar. Let's say if I move after I rotate the circles, then the position of A, let's say P in this position and P, it becomes in this position. So my questions, will it change the meaning of the sequence? No, the sequence won't change at all. However, you need to be careful. So my earlier example here is only using, I only use 2 points. Okay. If you use more than 2 elements in a circular permutations, you will know that you can see the difference because of the order, how you read the circular permutation. So circular permutations are to be read counterclockwise. It's not using a clockwise manner. So here I give you another examples. Let's say like earlier, I have 3 characters, 3 alphabets A, B, and C. So I will ask you guys to arrange these 3 characters in a circular permutation. So let's say I arrange it like this one. A on top of the circle, B on the right bottom, and C on the left bottom. So if I rotate it, oh, okay. So for this one, for this peculiar permutation, for this specific permutation, it will be called as ACB. Remember, circular permutations are to be read counterclockwise. So it's not ABC. If I read it ABC, it means it is clockwise, right? But since it is to be read counterclockwise, it becomes A, C, B. So if I rotate the arrangement of this to become like this one, C becoming to the top, at the top of the circle, and then A over here, and then B over here. Then A will become C, B, A. So ACB here with CPA here, they are equivalent. Be careful here. I'm not saying that they are the same, but they are equivalent. The symbol here is not equal sign, but this is the equivalent symbol. Right? So, okay, so what if I change the orders? Let's say here, like ACP, like earlier, ACP here is different with APC. It's not equivalent with APC. Why? Let's say ACP. no matter how many times that I rotate it. Let's say I rotate it 1 times clockwise here. Okay. Let's say rotate it clockwise like this one. It will become C, B, A. I rotate it again, it becomes B, A, C. So in that case, if I rotate it again, 0. Okay. If I rotate it again, it will return to its normal state like A, C, B. So the three variation earlier, they are the same. Not the same, sorry. They are equivalent. ACB equal with CPA equal with BAC. But it's not equivalence. They are, they are not it's not equivalent with this one. If I change it to BCA, if I rotate it BCA, it will become CAP. And then if I rotate it again, what will it become? It will become A, B, and C. You see, A, B, C, A, C, B. They are in a different order. They have different order. So you guys need to be careful with the circular permutation. Yeah, so for example, these questions for bridge players sit in a circular position. There are how many possible sitting arrangements, right? So there are much to be talked earlier, but it's good for you since you can just directly apply the previous formula, right? 4 minus 1 means 3 factorial. So we have only 6 possible sitting arrangements for these 4 bridge players. Okay. Group permutation is a permutation of n objects. It can be categorized in k groups in which there are n1 objects in group number 1 and n2 objects in group number 2 until nk objects in group number k. So the way how you compute the permutations of these group permutations, it will become like this one. So n, the total number of objects that you have, n factorials divided by n1 factorial multiplied by n2 factorial multiplied by n3 factorial until all the way that you reach nk factorial. So these are, if you are asked to count up the number of possibilities in a group permutation. Okay, here. Let's say I have 9 lamps are arranged in a series circuits on a Christmas tree. Then how many possible arrangements to put these 9 lamps on the Christmas trees if there are 3 lamps, 4 yellow lamps, 3 red lamps, 4 yellow lamps, and 2 blue lamps. So what are the answer? Okay. This one. So 9 lamps are arranged in a series on a Christmas tree. Then How many possible arrangements to put these 9 lamps on the Christmas trees if there are 3 red lamps, 4 yellow lamps, and 2 blue lamps?
8 factorial, sir.
8 factorials.
Yeah.
This one. Okay. Any other solutions? So where do you get this 8 factorial, Gabriel? From where?
I'm using the previous permutation that p equal to n minus 1 factorial.
P equal to this one.
Yeah, because
Mhm.
Christmas tree is, if we arrange lamp,
Mhm.
so it will arrange like a circle, sir.
Mhm.
Then I think I will choose this formula.
Okay. So any possible, any other solutions?
One thousand two hundred and
1260. So where do you get it, Kathleen? Where do you get this number?
9 factorial divided by 3 factorial
Wait,
times 4 factorial
three
times
factorial,
2 factorial.
this one. So this one's following the group permutation, right? Okay. So any other answers? Maybe you are using this formula. Maybe anyone is using this formula? No? No one? How about Kenneth?
I'm afraid to answer, sir.
You are afraid to answer? Why?
It will always wrong. No, I'm just kidding.
No, it's fine. Uh, don't be afraid. Don't be shy if your answer is wrong. It's a learning process. If you always answer the correct one, then why bother you want to learn something, right? So you want to learn something because you don't know about the things that you want to learn from. If you already know about that thing, then you can choose another subject that you still don't know about it. So it's fine.
Yeah, I think I'm gonna go with
If you don't have any idea, so from these two
yeah.
possible solutions, which one that you will go with?
The second one is Kathleen's answer, right, sir?
Right. This one is
Okay.
Kathleen.
I think I'm gonna go with
Gabriel, right?
yeah, I think I'm gonna go with Kathleen's answer.
You go with
It's pretty
Kathleen
convincing.
plus one. It sounds pretty convincing. Okay, how about the others like Kilang, Michelle, and Reinhardt?
I still doubt, sir.
Okay. So yeah, let me just answer this one. So actually for these questions here, you need to see. So even though that we know that we have 9 lamps to be arranged in on the Christmas trees, and then the argument from our friend Gabriel says that the Christmas tree, the shape is like in a round, right? Like a circle. So even though it's like similar like a circle, you need to read on the questions again. So is that the limitations on the questions? Is that only is the scope of the questions only ends until that point, or do they still have further requirements, right? So here you can see that the arrangements of these 9 lamps, you know that there are some other conditions. What are the conditions? You have 3 red lamps, 4 yellow lamps, and 2 blue lamps. So in this case, you can think of it like there is one group that have 3 elements. This one, box number 1, it contains of 3 elements, and then box number 2, it has 4 elements. Box number 3, it has 2 elements. So in this case, it is much more preferable if we choose to solve these questions using group permutation. This one. So that's why we can get these numbers, 1,260. Okay, thank you, Kathleen, and Kenneth and Gabriel. Right, so yeah. So far, any questions about permutations? I hope that you don't get confused, you don't get sleepy with this one, even though I know that it is a very old subject. But believe me that you will still find this kind of problems in this that can be solved in the applications of informatics engineering. So you will find a lot of this kind of problems that you can solve using permutations, using probability. No questions? Or do you guys get sleepy?
No, sir. More likely confused.
More likely confused? Which one? Which part?
I'm not confused. Maybe everyone confused.
Because we have like a lot of formula here, right? So one easiest way is you need to see the basic characteristic for each of the, let's say, the permutations, the complete permutations, partial permutations, and then circular permutation and group permutations. One basic characteristic that all of these share, all of these different types of permutation share is that no matter what kind of arrangement that you are asked to create, you need to consider the sequence, the order of how you do the arrangement. So these are the basic characteristics of permutation. So then if you already know these basic characteristics, then you need to see the problems, whether you need to arrange all the elements in a group. If you are asked to create an arrangement for all elements in a set, in a group, then it's easy. You can just directly go to the complete permutations or a normal permutations like this one. But if you need to make some arrangements with consideration some elements of that group, not all the elements of that group, but some elements of that group. So what does it mean? It means a partial, right? Not the whole groups, not the whole set, not the complete set. So it means a partial. Then you can just directly go to the partial permutation. Then if you are faced with the problems, you know that the shape of the problem is more likely in a circular shape, then you go directly to the circular permutation. Let's say select the seating arrangement around the round table, okay, or maybe like in the cube. So if it's in the form of cube, so what are the shapes? when people are queuing in the to buy a ticket. Let's say people wants to buy a train ticket at the train stations. So people needs to stand in a queue. In this case, so what will be the shape of this queue? Will it be in the linear form or circular form? So I'm not sure since it's in the pandemic, so we don't have like get many chance to travel around. So maybe before the pandemic, if there's any of you ever have the experience to ride on a train, to buy the train ticket in a train stations,
Online or offline, sir?
offline, obviously
Oh,
offline,
okay.
not
No,
online,
never.
never. So always online. Praise the technology, right? Thanks to the apps, thanks to the websites that you don't need to like queuing up on the train station.
And yeah, that's why we're here, sir.
Uh,
IT, right?
yeah, but if the problem is asked in the offline, so of course, so you choose the IT because you want to know to solve this kind of problem, right? So before you can create the solution for that problem, to create the software, then you need to know the basic of the problem, right? Before you create the online ticket selling applications, then what are the basis for that? Why do you want to come up with this kind of applications? Because you want to reduce the number of people lining up in a queue, right? Just to buy the ticket. So in that case, you know that this kind of queue, it will looks like whether it's in a linear form or a circular form. Okay, back to my earlier questions. So in this case, like in the traditional, in the offline ticket selling booth, so usually it will follow up in the linear form, not in a circular form. So in that case, it should be easier for you to uh, to decide whether you should use complete permutations or a partial permutation, right? So yeah, like earlier, Kenneth, right? You say that because you choose the IT, you choose to join in the informatics engineering department because yeah, you want to use the technology to make people's life more convenient, right? To use the technology to do many things. But before you can do that, before you solve this kind of problem, before you come up with the solutions, then you need to know what are the source of your problem. What is the original problem will look like in the real world. Otherwise, if you don't know like the source of the problem and then you just come up with like some kind of apps, but you don't know whether the problem that you want to solve, then why do you bother? Why do you bother to spend your time, to spend your energy just to create this kind of app that is unclear what kind of problem that you want to solve? Yeah. So this is just uh, some words that I want to share with you guys that you should think about, that you can think upon. Okay. So as you go through study in this informatics engineering department, so when you want to create like this kind of application or the software, you should also consider like what kind of problem that you actually want to help to solve in the real world scenario. So in that way, the application of the software that you come up with is real, it will become really meaningful, not just like some Hogwarts applications that does not solve any problem at all. Okay, so yeah, for page player here. So of course it's circular. Okay, let me just continue. Group permutations, we finish it. Now combinations. Here, combination is another term. So I hope that you guys can still bear with me for several minutes. We still have 7 more slides. The total slides for today's topic is only 41 slides. And now we are in slide number 34, so it should not be that long anymore. Okay. Okay, so we go with the combinations here. So you know that for the permutations, you are asked to create any possible arrangements with regard to the sequence or the order. What if you don't need to consider about the sequence or the order of such arrangements? So for this kinds of problem, it is more known as the combination problem. So here, the symbols, the mathematical symbols is using C and similar like permutations. So how many cases, how many elements out of the number of sets that you have. So basically here it's similar to permutations. Basically it's similar with permutations, partial permutations to be bluntly. Partial are permutations of n. But since in permutations you need to consider the sequence, in combinations, however, you don't need to consider about these kinds of the sequence. So the formula here should be modified a little bit to become like this one. C R combinations out of n will become like n divided by r factor n factorial divided by r factorial multiplied by n minus r factorial. So for example here, like how many possible arrangements to choose 3 menus out of 11 available menus in restaurant. So for these questions, okay, so sorry, there's some error here. Right. So for these questions here, so you already know from the answers that I provide here is should be solved using combination. But I want to ask you to think in much more deeper regarding these questions. Okay, so that you can decide, that you can determine whether this solution, this problem, this question should be solved using permutations or combinations. Here is the deal. So if you choose a menu on the restaurant, will this sequence matter? Like the dish that you choose, will the sequence matters? I'm not talking, of course, if we are talking like a fine dining experience, like you have the appetizer, you have main course, you have desserts, right? Then the order, the sequence is matter. But like let's say, even though in the appetizer, right? There, it usually the restaurant will have several selections of appetizers that you can choose. For the main course, of course, there are also several options that you can choose. For the desserts, it's also the same. Okay, so let's say I'm asking you to choose for the main course. Will these selections of your main course affect the way how you eat? Let's say the restaurant, they have, let's say 5 selections of main course. And then you can choose 2 out of 5. Will it matter for you? Let's say you choose number 1 and then you choose 3, or if they come up first with, they give you 3 first and then 1. Will it matter for you? Let me, okay, let's say choose 2 out of 5 main courses. Let's say what are the foods that you guys make like to eat. Then let's say tenderloin steak, and then chicken 2. Oh, sorry. I'm not sure if any of you are Muslims. No. Yeah, I don't. I just give like some kind of a random thesis, right? So it does not mean that you should choose like this one. For example, like this one. Pork knuckle, and then we have like Cantonese roasted duck. Let's say in a restaurant, it has 5 options of a main course. Okay, let's say here, let's say you choose this one, chicken stick, and also you choose, let's say, Cantonese roasted duck. Will it matter for you? Let's say if the waitress serve you the Cantonese roasted duck first and then chicken stick. They bring them out to you. Let's say you order chicken stick and then Cantonese roasted duck, but if the waitress give to you Cantonese roasted duck first and then chicken stick, will it matter for you? Yeah, usually it will not be matter, right? Usually it won't matter at all. So if you know that it won't matter, it will not have any effect. So in that case, it is safe for you to assume that this kind of questions can be solved, should be solved using combination, not permutation. But if this one, like let's say they have like this kind of order, let's say don't have a pork knuckle. Let's say here is a cream soup, and then let's say I have like fruit ice cream, like this one. If it has like this kind of orders, like in which the food should be served, it has a correct sequence like appetizers, main course, and dessert. So in this case, then it is clear that you need to consider the sequence. The waiters, they need to serve the dishes in the correct order, in the correct sequence. In that case, if the question is like this one, so you know that it should be solved using permutation, uh, using permutation formula. Okay. Yeah, so yeah, this is examples, another example. So using the previous permutation examples, so how many combinations can be made for 2 out of 4 different characters? So it's regardless of their orders. This one. How many combinations can be made 2 out of 4 different characters regardless of their sequence? So in this case, okay, so let's solve it in the full way. Okay, we have AP, AC, AT, and then we have the second character P, PA, PA with AP. Regardless of the sequence, it means PA and AP, they are the same. So we can remove this course of action. PC, PT, and then we come up with T. CA is similar with AC, then we need to eliminate these options. CP similar with PC. Similarly, we also need to eliminate these options. We have CT, and then T, since all the other characters combinations has been used, then T, we don't need to do anything at all. So in this case, you will know that you will end up with only 12 combinations. Sorry, 6 combinations. Much smaller compared to the one if you need to consider the sequence of the order. So similarly with permutations, combination itself has there are various types of combinations. For example, like this one, K combinations with repetitions, or in some reference book, in some textbooks, it is also known as K multi combinations. So for this one, you are asked to create for any possible arrangements that can be made to arrange K elements where K itself is not necessarily distinct. K itself can be a repeated element, can be a duplicated element from the overall n objects or n elements of a set, regardless of their sequences. In this case, it will be the formula here. The normal formula of combinations here is only like this one, right? Actually, K combinations of n. But since you should also consider if there is any repeatable elements. So in that case, the number of sets that you will have here, the overall sets will also increase. How much? K minus 1, based on the number of K elements that you want to arrange. So it will then, therefore, the previous formula will becomes like this one. N plus K minus 1 factorial divided by K factorial multiplied by N minus 1 factorial. Okay, so where this formula come from? So there is some proof to get this formula, but I don't think that you are very interested in doing this kind of proving. So let me just skip the proving part and just directly go to the examples. Okay, like this one. So how many combinations can be made for 2 out of 4 different characters, for example, A, B, C, D, where duplicate characters could occur? For example, here, A is possible for A to be matched with A, becoming AA. For B, similarly, it's possible for BB, C, CC, D with DD. Okay, originally you should only have 6, right? 1, 2, let me drop this one. Okay, 1, 2, 3, 4, 5, and 6. But since now you need to include the repeated elements such as AA, BB, CC, or DD, then the numbers 6, the original 6, needs to be added with another 4. So it will end up with 10 possible arrangement, 10 possible combination. So, okay, so we want to check using the previous combination formula here from this slide. So we inserted 4, C4 plus 2 minus 1 divided by 2 factorial 4 minus 1. So 5 factorials divided by 2 factorial is 2, multiplied by 3 factorial, so it will become like this one. It will become 10 for its final result. Okay, so for example, this one, 3 dice are tossed at the same time. How many possible distinct outcomes from this experiment? Three dice are tossed at the same time. How many possible distinct outcomes from this experiment? Don't worry, we still have another one slide left. So after this should be finished, and then we can go to the individual practice. So the explanation will be finished after, probably should be finished after this slide. This should be the last slide. With the next slide shows you the solution. So before I open up the solution, so someone maybe wants to give the answer. Or let me just open up the solution right now. Okay. Yeah. So, okay. So now we have the solution is like this one. So, how many the possible outcomes that we can get from one die, from a die? So the questions here is you will be asked to throw 3 dice, right? But you need to consider for one die, how many sides that it has. For each side, it will have only 6 sides, right? So there are only 6 possible number of I in a die. So how many experiments that you will be asked to do? In one experiment, you will be asked to toss 3 dice, throwing 3 dice. So the number of R here is 3. So you'll be asked to do 3 combinations out of 6 possible solutions while allowing duplicates to happen. So in this regards, the answer will be like this one. So 3 combinations out of 8, 8 here coming from 6 added by 3 minus 1. So 8 factorial divided by 3 factorial, 5 factorials, and you will have 56 for the answer. All right, so this is the last slide for this topic. Any questions so far about experiments and then sample space, outcome, permutation, combination? We haven't reached the probability. So even though the title for this PPT is probability, but it's still part 1. So we haven't touched the probability part at all at this point. So we will talk more about probability in the next week lecture. Any questions?
Excuse me, sir.
Yes, Gabriel?
So if we toss 4 dice at the same time, so the K is 4.
Right.
Oh,
So let's say this one, right? We have 4 dice. So in this case, K or R becoming 4.
thank you, sir.
You're welcome. No other questions? Clear. Okay, so we have the self exercise here. We have 4 questions. Right, maybe you want to take a screenshot first for the questions. 1, 2, 3, 4. Maybe we only need to do 2 questions considering the time. So how about question number 2? Okay, question number 2 AP and also number 4. Let's do questions number 2 and number 4. So this is question number 2. Let me copy this one first. And this one. This one and question number 4. So these two questions.
Sir, for the number 1B,
Yeah.
for the vice president, is it allowed to have multiple people?
Yes, it can be a multiple people. So you guys already screenshot the questions, right? Okay. Oh, if you haven't screenshot the questions, then I will put the questions in the chat room. Oops, too messy. This one and this one.
Sir, for the car is duplication allowed, sir.
Sorry.
For the vehicle question is duplication allowed, sir.
Yes.
Sir, thank you.
You're welcome.
Sir,
Yes.
about the vehicle's license plate number,
Hmm.
is it in Indonesia or outside Indonesia?
In Indonesia.
If it's Indonesia, then it is not possible for us to put zero in front. Is that correct?
Sorry. Which one?
For in Indonesia,
Mm-hmm.
if you said that this plate number is in Indonesia, that
Mhm.
is it this it is not possible for us to put 0 on the first number. Am I correct?
Actually, I'm not quite sure about that, but presumably that it's allowed for you to put 0 on the first number. Presumably,
Is it allowed?
uh, I'm not sure about the legal, like in the Indonesia, but assume let's let's assume that it's allowed for these questions. So if you
Okay.
want to ask like the real scenario, like in Indonesia, whether it's allowed for you to put like 0 as the first character, sorry, as the first number, the first digit in the number part. So whether it's allowed or not, then we need to look at the regulations from
Okay.
the police. But I'm not talking about like whether these possibilities is allowed or not.
Okay, sir. Thank you.
Okay. Okay, so okay, let's see. So Gabriel number 215. 26, 9, 10, 10. Okay, so yeah, so if we are considering like maybe it's like Gabriel for you, 26 times 9 times 10, 10, 10 times 26, 10, 26, 9 is because you assume that 0 is not allowed as the first digit, right? Am I correct? Yeah, if that is the case, then it's correct. But since there is no such information in the questions, then it's assumed that 0 is allowed as the first digit in the number part. So in that case, Kathleen's answer is the correct one. So actually for question number 4 itself, it's not really based on, you cannot just solve it using any permutation or combination problem, but you need to know like how many possibilities of value that can be put at that place. So 26 of the first alphabet, first character alphabets, and then follow up by 3 digits numbers. For each number, you will have like 10 possible values starting from 0 to 9. Okay, and then follow up by two alphabets, 20 times 26 times 26. Yeah. Okay, and then okay, so Gilang, what 60 possible arrangement? So for number 2 here, let me go back here. Right. So for number 2 here, we have two questions A and B. So which one that do you mean for 60? Gilang?
Yes, sir.
So you answer for number 2 is 60 possible arrangement, right? But for the
Yes.
number 2, we have two questions, 2A and 2B. Which one
Oh,
is it?
it's the 61 is for 2A.
2A.
I'm sorry.
Okay. So, okay. And 2B. So anyone? Yeah. So actually, yes, 2A is correct, 60. For 2A, yeah. Let me see. Maybe this one, right? Which is, yeah. Okay. So yeah, everyone can see the screen now. Okay, yeah. For 2.8, remember, so we already have 5 students of the members. We need to put these 5 students into their corresponding positions, such as president, vice president, and also secretary. So there are, presumably, there are only 3 positions, right? Presumably, there are only 3 positions, assuming that each one is only one. So 3 permutations of 5. So we will have like the 60 possible combinations of students, assuming we will have like one president, one secretary, and another one is the vice president. So the second questions for 2B, what if only one person is allowed to be the president and only one person is allowed to be the secretary? So there comes another question. What if, presumably, the other 3 students can become the vice president? Sometimes it's possible for the vice presidents to be both held by multiple persons, right? Multiple persons hold, let's say, vice president 1, vice president 2, and vice president 3. Okay, so in that case, we need to perform group permutations for this to be. So we'll have 5 factorials divided by 1 factorial multiply 1 factorial multiply 3 factorials. So we'll have 20 possible combinations for this one. Okay, so yeah, any other questions before I close these sessions? Or do you want to do the other questions, question number 1 and 3 too, or maybe you want to take some rest before the next class if you have next class?
Um,
Yes,
is it sixer?
which one?
Number 3.
Number 3. These 5 members will represent of 5 minutes. However, if the president and vice presidents always sit side by side. Okay, so I found this in a circle, so it should be the circular permutation, right? Should be so.
No, wait,
Yes,
sir.
using the circular permutation and -1 permutation. It should be like 4 factorials. If it's only this one, but we have another conditions here. Wait,
Friend, for number 2, is it because for the circular it's always -1
yes.
because
Mhm.
there's only one for the point of like our point for counting start the count. So because in number 3 the president and the vice president always sit side by side, can we assume that we can just -2 for it, sir?
No, it will be a difference because here is let's look at here. Actually, number 3 it's quite tricky. This one is quite tricky for number 3. So you cannot just assume like for, let me go back to the circular permutation here, this one, right? So for the circular permutations, the formula is n minus 1, with n is the number of elements, right, in the circular order. However, in the question number 3 here, we have 5 members, and then how many possible sitting arrangement if president and vice presidents always sit side by side. Okay, so let me make another. Let me put another slide here. Okay, let's say I have this one. Presidents, this one. Vice presidents. Earlier from the question number 2, it is safe for us to assume that there can be 3 vice presidents, right? So we can say that and then the last one is the secretary here, right? Like this one. So let's say we have this one. So actually you can already guess from my picture here, no matter how you put the president here, he will always sit right beside his vice president, right? If, let's say, it is rotated, let's say it's rotated into this one, still the president still sit beside his vice president, right? So the similar case, let's say if this one I want to change, this was not presidents, but this one is vice president number 2. So this one is the president. Since we know that we only have one president, one secretary, so it's safe to assume that the other 3 can be the vice president. So this is also correct, this kind of arrangement. The same also applies if I put it here, presidents, this one is vice president number 3. In this case, no matter your arrangement here, the president will always sit right beside his or her vice president. So in this case, it will always be n minus 1, not n minus 2. So it will be 5 minus 1 factorial. So 4 factorial. There will be 24 possible sitting arrangement.
No one ever told us about the 3 vice presidents, sir. I thought there are at least 1 or 2 vice president.
Yeah, so in that case, you can put like include in your assumption. So from here, from the question number 2, we know that president, vice president, and secretary. So from 2P here, we know that only one person allowed to be president and one person allowed to be the secretary. So it means that it is safe to assume that the other 3 can be the vice presidents. As long as this one, number 2 here, no student hold multiple position. But it can be for the other persons to hold the same position. Let's say here I have five students. Okay. Let me just borrow your name, if that is all right. Okay, I borrow your name. Let's say.
Oh, that's
Kenneth.
fine, sir. Don't worry.
All right. I have Kenneth, Alex, and then I have others. Let's say, and then okay, and then we have others like, okay. Oh, presumably is not here. So let's say pick all the student name, like this one. Let's see from the first question, from 2A here, there is no student hold multiple position. What does it mean? Let's say Gilang. If Gilang has been chosen as the president, then it is not possible for Gilang to be the secretary or to be the vice president. That is the condition for 2A. But for conditions to be here, only one person is allowed to be president and only one person is allowed to be the secretary. So it means, let's say that Gilang here already be the president. It means Gabriel cannot be the president. Gabriel can only be the vice president or the secretary. But let's say, okay, let's say Gilang is president, Gabriel is the secretary. So we already have these two conditions hold according to the requirement here. So we can match up, let's say Kenneth, Michelle, and Kathleen here becomes the vice presidents. Let's say, since it is too confusing, right? So that's why in my earlier picture here, I separate into vice president 1, vice president 2, and vice president 3. Let's say Kenneth become 1, Kathleen vice president 2, Michelle vice president 3. So in this case, it does not matter. The question here is still holds, the requirement still holds true, in which there is no student that hold multiple position. We don't have one student have two positions, right? And the number of students who hold the position of president and secretary is exactly 1. So in this case, this kind of arrangements is possible. Or let's say this is the arrangement 1. Let's say, for example, we have like this kind of arrangement, Michelle, and then let's say Gabriel, we change to like this one. This is the second possible arrangement, right? The president is Michelle, secretary is Kathleen, vice president 1, Kenneth, Gabriel, Gilang. Or the next arrangement is, okay, Gilang is secretary, Kathleen is the vice president, or maybe Kenneth is the president, Michelle is the vice president 1, right? So this kind of arrangements still match with this requirement. Any other questions? Or is it gets confusing?
It's a bit confusing, sir, but yeah, I get it.
Yeah. So as long as the condition here is met, is fulfilled, is satisfied, then for the other, it is safe for you, for example, to assume that there can be 3 vice presidents for this student council. Okay, so yeah. So I'll let you guys to think about it a little bit, maybe because this topic is only reviewing some of the material from your senior high school. So maybe you can do a little bit more reviewing and then see do the other exercise here first. Like then we only have exercise number 1 in that case. Yeah. So if and exercise number 1 is relatively easy. It's a 5 out of 11, 5 permutations of 11, or you can also say 5 combinations of 11, because at this time you don't think that the sequence is matter. For this one, this one is more likely for you to solve using combinations, because at this time you don't need to think out about the sequence, about the order. Right. If there are no questions, then yeah, we'll see you. Okay. Before I forget to mention, we have the first assignment already. It's in the ULS, already been uploaded. Okay, so you go to the ULS and then you will see. Oh, I need to enable this setting first. Right. Where is it? Okay, so yeah, the first assignment has been uploaded in the ULS, and then you need to finish this first assignment about mathematical induction and pigeonhole principle from last week's topic. So the due date is 1 week until 26 April. And then the time limit to attempt the homework here is 45 minutes. So any late submissions will be regarded as 0. Okay, try your best to finish this assignment. If you don't have any other questions, then yeah, we'll see you again in next week class. I will also upload the PPT on the URS after this class. Okay, so yeah, so see you again next week.
Thank you, sir.
You're welcome.
Yes, sir.
You're welcome.